Hello, I'm Aaron Lohr.
And I'm Caitlin Ondrachek.
And this is the Endocrine News Podcast.
Today I'm speaking with Dr. Nayara Aquino, professor at Federal University of Minas Gerais in Brazil, where she studies neuroendocrine control of the female reproductive system. Her endocrinology paper, Alpha estrogen and progesterone receptors modulate Kisspeptin effects on prolactin, role in estradiol-induced prolactin surge in female rats, was selected for the Women in Endocrinology series. I hope you enjoy our conversation about her work. This work seemed to highlight that there is more to this population of neurons than previously thought. Can you provide a big picture overview of this study, as well as give me a little bit more background on this protein, Kisspeptin?
Yeah, Kisspeptin is a very important protein that was previously related to the release of luteinizing hormone and the control of reproduction. But besides that, we work with Kisspeptin and the control that Kisspeptin has on prolactin secretion. So previously, we have demonstrated that Kisspeptin can increase prolactin secretion, and it's dependent on estradiol. So just in overactomized rats treated with estradiol or in proestrus rats, the intracerebral ventricular injection of Kisspeptin can increase prolactin secretion. It was really interesting in this work because we demonstrated the receptors involved in this process. So we demonstrated that the estrogen receptor, alpha, and not the estrogen receptor beta, it's responsible for modulate this interaction between the ovarian steroids and the Kisspeptin effect on prolactin. Moreover, we showed that when we treated these rats with estradiol plus progesterone, we had a potentiation of this effect, something like more prolactin release than the animals just treated with estradiol. So we could provide evidence that Kisspeptin can increase prolactin secretion, and this effect is dependent on the estradiol receptor alpha and not beta, and is potentiated by progesterone. Moreover, it's interesting to look that we treated these animals with a new drug, the antagonist for the Kisspeptin receptor. We call this the Kisspeptin 234. And we treated the animals with this antagonist, and we looked for the prolactin surge, the physiological prolactin surge that is induced by the estradiol during the afternoon. And we saw that when we blocked the Kisspeptin receptor, we could impair the early phase of the prolactin surge, and we could avoid the LH surge. So we could see that Kisspeptin is also important to control this physiological release of prolactin induced by estradiol.
Can you tell me a little bit about how you performed these experiments? What was the initial setup?
Well, we used Wistar rats. First of all, we overactomized these rats, and then we treated these rats with estradiol. Another group we treated with estradiol for 3 consecutive days, and in the 4th days we inject progesterone. Then a little time later, we injected Kisspeptin intracerebral ventricularly, and we made some blood collections, to study this profile of prolactin release. And it's really interesting in this paper because we used a new or something like new way to have these blood collections. We use the vein cannulation, but here we use tail tip blood collections. It was a way to have blood that have been performed before for mice, but never for rats. And we used this here, and it was really nice because we could have a small amount of blood, and we could measure prolactin with this small amount through analyzer that we developed here in our lab. So it's really interesting because we can avoid some surgery, and we saw that there is no stress for the rats since we have previously acclimated them to the method.
Is this technique, the tail-tip blood collection, does that help to reduce the stress in the animals? I would imagine that's important for these kinds of studies.
Yeah, it's really important because we know that prolactin is a hormone that is influenced by stress. And always I have some papers published that we use the jugular vein cannulation. We saw that it's not so much stress with this method, but we need to make a cannulation, anesthesia, surgery. So we decided to use this tail-top blood collection that has been previously used for mice. We decided to test this for rats. And we needed to acclimate these rats 30 days, something like 1 month before the experiment. And in the day of the experiment, we clipped something like 1 or 2 millimeters of the distal part of the tail. And we took something around 10 microliters of blood. We could use just 10 microliters of blood to make all the measurements. So it's really, really, really interesting. And we saw that our measurements was really, really near of the values that we used before doing the veil cannulation and measured the hormones by red immunoassay. There is another thing that we did in this study that is really interesting because we developed ELISA to measure prolactin in the rat. It was an assay that has been previously done in the mice, but never in the rat. And the great thing here is that before we used it to use red immunoassay to make the measurements. And now, since we could use an ELISA, we can reduce the volume of blood that we need. So if before we needed something like 100 microliters, with the ELISA we just need 10 microliters. So it's really good.
I'm curious as to, so you said that the actual estrogen receptors, the subtypes that you found in this experiment, it was specific to ER alpha. Was that a surprise to you that it was not ER beta as well?
Not so much, because we know that estrogen receptor alpha exerts a lot of functions in the reproductive system, in the female reproductive system, mainly controlling the feedback of estradiol to the luteinizing hormone. The estrogen receptor beta has another functions in the male reproductive system and also in the ovaries, but we could expect that estrogen receptor alpha could be more responsible for this effect. And in fact, it was what we saw with this study.
So I'm curious a little bit about this antagonist that you used, the Kisspeptin 234. So you were looking at the effect of this drug on estradiol-induced surges of prolactin and LH. Is that correct?
Yeah.
Can you tell me a little bit more about what the results were and what the significance of this was?
This Kisspeptin 234 is a recent drug. It's not so much new nowadays, but it's an approach we can use to evaluate this Kisspeptin, dopamine, and prolactin system. We saw that when we used this antagonist, we injected this intracerebroventricularly. When we used this, we could block the effect of Kisspeptin. And when we used this during the afternoon, this prolactin surge induced by estradiol, we could impair the early phase of the prolactin surge. So the early phase was really smaller, and then the second phase was something equal. But we could completely prevent the luteinizing hormone surge induced by estradiol. And we have just published another paper in endocrinology, and we used this antagonist again, and we could prevent the effect of Kisspeptin on prolactin secretion. When we inject Kisspeptin intracerebroventricularly, we can see a prolactin secretion something around 5, 10, or 15 minutes later. And this can be prevented by the treatment with Kisspeptin 234, showing that the receptor for Kisspeptin, the Kis1R, and the action of Kisspeptin in this receptor is essential for the increase of prolactin.
what is the takeaway message from this work? I guess the 2017 paper, as well as your most recent paper. Can you place this into a broader context and also talk a little bit about where this research is going to go next?
We know that prolactin is essential for a lot of reproductive and also non-reproductive functions. Regarding the reproductive system, we know that prolactin acts as a luteinotrophic hormone, is essential for proper luteal function and also for fertility. In fact, we know that chronic hyperprolactinemia is a common cause of infertility worldwide. So I think that's why it's so important to study and to understand how prolactin secretion is controlled. We know that this hyperprolactinemia can be treated with dopamine agonists, but sometimes the treatment cannot be so good, and sometimes this patient can have some collateral effects that we can try to avoid. So if we understand how the prolactin secretion is controlled, how Kisspeptin neurons can control the dopamine release, we can think about treatments for hyperprolactinemia, for infertility, and we can try to understand how these things work. In fact, we are working now to try to understand more. So in this paper that we published, we showed that Kis1R is important, the receptor for Kisspeptin is important to the effect of Kisspeptin on prolactin secretion, but not in the control that Kisspeptin can make in dopaminergic neurons. So we are trying to understand how this pathway works, because after that we can try to make something around these dysfunctions and diseases.
Can you tell me a little bit about how you're planning on dissecting this pathway?
We understood that the injection of Kisspeptin and Kisspeptin can increase prolactin release. And this is dependent on the Kis1R, the Kisspeptin receptor. But Kisspeptin increases prolactin release through an inhibition of the dopaminergic neurons, the tuberoinfundibular dopaminergic neurons that we know as TIDA neurons. We now know that the effects of Kisspeptin on prolactin secretion is dependent on the receptor for Kisspeptin, the Kis1R. But the effect of Kisspeptin on TIDA neurons is not dependent on Kis1R. In fact, we have shown that these TIDA neurons do not express Kis1R, and we have shown that Kisspeptin cannot act directly on these neurons using patch clamp. We now know that Kisspeptin cannot act directly on these neurons, and we suggest that Kisspeptin is using an indirect pathway to control dopaminergic neurons and prolactin secretion, or Kisspeptin is binding to another receptor that not the Kis1R. So I am now investigating another receptors, like the receptor for neuropeptide FF, looking if Kisspeptin can control the dopaminergic neurons and the prolactin secretion through the receptors, and trying to understand better how this pathway can work in physiological ways.
Do you have plans to follow up whether there's also this indirect effect of Kisspeptin?
Yeah, we think that perhaps oxytocinergic neurons can participate in the process, so we have plans to investigate that as well. I think it's interesting to think about this mechanism that control prolactin system. So perhaps I think we should look for the estrogen receptors to the progesterone receptors to try to help people that are suffering with infertility worldwide. And I just wanted to say thank you for the highlight, and I think it's really important to look to women in science as well, because sometimes we are just involved in a lot of things with home, with children and everything. So it's really interesting to look to women in endocrinology and women in science. So I just wanted to say thank you as well.
Oh, well, it's our pleasure. It's been very exciting to have your work highlighted as part of our Women in Endocrinology collection. And speaking of which, is there anything that you'd like to share about your own personal experience as a researcher in this field?
Well, I started working with Kisspeptin and Prolactin in 2011, and I did a master and a PhD in this area, working with Professor Rafael Shefka here in Federal University of Minas Gerais in Brazil. Then I moved to work with Professor David Gretton at the University of Otago in New Zealand. And we always tried to understand how this prolactin pathway works and try to understand the dysfunctions that we can observe in this pathway. I learned a lot here in Brazil. I learned a lot here in New Zealand. And then I returned to Brazil and I got a position as a substitute professor at the Federal University of Minas Gerais. And now I'm working there, teaching classes, continuing the research, and hoping that soon we can understand totally how this pathway works and we can help people with some problems with prolactin and infertility.
I just wish you the very best of luck with your research as well as your teaching. And thank you very much for your time. I learned a lot, and I really appreciated hearing you tell me about your research.
Oh, thank you.
That's all for this podcast. Thanks for listening. To learn more and to find links to Dr. Aquino's paper and the Women in Endocrinology series, you can find this episode on our webpage, www.endocrine.org/podcast. There you can also listen to our previous episodes. Thanks again for listening.
Endocrine News podcasts are a free service of the Endocrine Society. To learn more or to become a member, visit the Society's website at www.endocrine.org.